over in Europe. And inside, there's this incredible machine designed to smash together the tiniest bits of our universe.
That's the Large Hadron Collider, the LHC at CERN. Yeah, it's really quite something.
It absolutely is. And for this deep dive, we really want to take you step by step right into the heart of it. What actually happens when those particles collide?
Yeah, our sources give us a fantastic, detailed look. And our goal here is to sort of break that down, make it clear, engaging. Hopefully you'll feel like you've got a ringside seat for a subatomic smash-up by the end.
Exactly. If you've ever wondered how scientists actually, probe the very foundations of reality, this is definitely for you. We'll try to unpack it without drowning in jargon. There are some genuinely fascinating bits.
Definitely.
Okay, so let's start right at the beginning. These particles, they smash together. Where do they even come from?
All right, good question. It usually starts pretty simply. For the proton collisions, which are very common, the source is just hydrogen gas. They strip the electrons off the hydrogen atoms, leaving the protons.
Just the nucleus, the proton.
Exactly. Or for different experiments, maybe studying conditions like the early universe, they might use heavier things like lead ions. They strip electrons off lead atoms too.
Okay, so you have these protons or ions, but they're not exactly whizzing around at light speed yet, are they? They need a serious ramp up.
Oh, absolutely not. They start off with relatively low energy. They have to go through this whole chain of accelerators before they even get near the main LHC ring, that big 27-kilometer one.
Like passing a baton in a relay race, but for energy.
That's a great way to put it. Yeah, it's a sequence. First, there's LINAC 2, gives them an initial push, then into the Proton Synchrotron Booster, then the Proton Synchrotron, the PS, and finally the Super Proton Synchrotron, or SPS.
Wow, okay.
Each stage adds more energy, refines the beam, gets them going faster and faster.
So multiple boosts before the grand finale, and then these highly energized particles, two separate beams of them, get injected into the main LHC ring, traveling opposite ways.
That's right, into two separate beam pipes running parallel inside the main tunnel, which is about 100 meters underground. They're going in opposite directions, getting ready for that head-on collision.
It sounds almost like a drag race setup, but, circular and underground. How do they actually get them up to those insane final speeds in the main ring?
Well, it involves these things called radiofrequency cavities spread around the ring. Think of them like energy stations.
Okay.
As the bunches of particles fly through, these cavities give them a precisely timed electromagnetic kick, boosting their energy with each lap.
A kick, okay. But keeping particles going nearly the speed of light in a circle, that must take some doing. That involves those super cold magnets, doesn't it?
Exactly. This is where the superconducting magnets come in. Thousands of them. And yes, they are incredibly cold. Minus 271.3 degrees Celsius. That's only 1.9 degrees above absolute zero.
Colder than outer space? Why so cold?
It's crucial. At that temperature, the materials in the magnets become superconducting. They conduct electricity with basically zero resistance, zero energy loss.
Right, no wasted energy means.
Means you can run huge electrical currents through them, generating incredibly powerful magnetic fields, far stronger than conventional magnets could manage without melting.
And these super strong fields are what steer the particles?
Precisely. They bend the path of the charged particles, keeping them confined within those narrow vacuum pipes, forcing them around the 27-kilometer circle instead of flying off in a straight line.
And they are really flying. The sources said something like 11,245 laps per second, reaching 99.9999991% the speed of light.
It's mind-boggling speed, yeah. The kinetic energy packed into each particle at that velocity is immense, especially considering how tiny they are.
Okay, so you've got these incredibly fast beams guided by super cold, super strong magnets. Now, getting them to actually hit each other, particles are tiny, space is big, even inside a pipe. How does that work?
Good point. That requires some very clever focusing just before the collision points. They use special magnets, quadrupole magnets essentially, to act like lenses.
Lenses for particle beams.
Kind of, yeah. They squeeze the beams down, making them incredibly narrow, thinner than a human hair, right at the specific points where they want the collisions to happen. This dramatically increases the probability that particles from the two opposing beams will actually collide.
Okay, so they focus them down tight, and these collision points aren't just anywhere in the ring, are they? They're inside those giant detectors.
Exactly right. There are 4 main interaction points where the beams are made to cross. And built around these points are the massive particle detectors, ATLS, CMS, LHCb, and ALICE.
Right, I've heard those names. Do they all do the same thing?
Not quite. ATLAS and CMS are sort of the general-purpose giants. They're designed to look for a very broad range of physics. The Higgs boson was discovered using them, for example. They look for anything, really.
Okay. And the others?
LHCb has a more specific job. It focuses on studying particles containing beauty quarks or B quarks. Studying their decays helps us understand subtle differences between matter and antimatter.
Interesting. And Alice?
Alice is different again. It mainly studies collisions of heavy ions, like those lead ions we mentioned earlier. These collisions recreate, for a tiny fraction of a second, the conditions of the very early universe, a state called quark-gluon plasma.
Wow, like a little Big Bang?
In a way, yes. Studying that plasma tells us about the fundamental state of matter at extreme temperatures and densities.
So the squeezed beams cross inside one of these detectors. They collide head-on. What actually happens in that instant? You have all this energy.
This is where Einstein's E mystery really comes alive.
Mm-hmm.
All that kinetic energy from the two colliding particles gets concentrated into an absolutely minuscule volume.
Tiny space, huge energy.
And in that instant, that concentrated energy converts directly into mass. It creates new particles. The energy literally materializes.
According to the equation.
Exactly. In the proton collisions, the total energy available for creating new stuff can reach up to 13.6 teraelectron volts, or TeV. That's a huge amount of energy on a subatomic scale.
So it's not just breaking the original particles apart, it's actually creating new ones from the collision energy itself.
That's the key point. It's creation from energy.
Mm.
And the conditions of the collision point are extreme. Momentarily, it's like a tiny fireball, incredibly hot and dense, mimicking conditions just fractions of a second after the Big Bang.
A subatomic fireball. And what kind of particles emerge from that?
A whole shower of them. You get the particles we know from the standard model of particle physics. Quarks, which make up protons and neutrons. Leptons, like electrons, and their heavier cousins, muons and neutrinos.
Uh-huh.
And the force carriers gauge bosons like photons, the W and Z bosons responsible for the weak force, gluons carrying the strong force, and of course the Higgs boson itself can be produced.
The Higgs. But I guess a lot of these particles created in the fireball don't last very long.
That's right. Many are highly unstable. They exist for just, unimaginably short times, fractions of a billionth of a second, sometimes much less before they decay into other, more stable particles. It's a cascade.
A rapid decay chain.
Exactly.
And this is really where the excitement lies for physicists, isn't it? The chance that maybe, just maybe, something else pops out of that fireball. Something unexpected.
Absolutely. That's the big hope. While seeing standard model particles confirms our theories, the real thrill is the possibility of creating something new. Exotic particles predicted by theories beyond the standard model.
Like what, for instance?
Well, things like supersymmetric particles, hypothetical heavier partners of the known particles, or maybe even particles that could make up dark matter, this mysterious stuff that seems to dominate the universe's mass, but we can't directly see.
So the LHC could potentially create dark matter particles right there in the detector.
That's one of the major goals. Finding particles like these would be revolutionary. It would be one of those huge aha moments in science, opening up entirely new chapters in physics.
Okay, so particles smash, energy becomes mass, new particles fly out, many decay instantly. How on earth do they see any of this? It's happening incredibly fast in a tiny space. That's where the detectors, like ATLAS and CMS, come in. You said they were like onions.
Yeah, that's a good analogy.
Yeah.
They're built in concentric layers around the collision point. Each layer is designed to do a specific job, to measure different properties of the particles flying out.
So starting from the collision point outwards, what's the first layer?
The very inner layers are tracking detectors, usually silicon pixel and strip detectors. They're incredibly precise. Their job is to record the exact path, the trajectory of charged particles as they fly away from the collision.
Like seeing tiny vapor trails.
Sort of, but electronically. This allows physicists to reconstruct where the particles came from the collision point, or vertex, and where they're going. And there's a clever trick here.
Oh.
These inner detectors are usually sitting inside a powerful magnetic field generated by a solenoid magnet within the detector. Charged particles bend as they move through a magnetic field.
Right, like the magnet steering the beams in the main ring.
Exactly. By measuring how much the track curves, physicists can determine the particle's momentum. More curves means less momentum, straighter means more. And the direction of the curve tells them if the particle's charge is positive or negative.
That's ingenious. So path, momentum, and charge just from the inner layers. What about figuring out what the particle actually is?
For that, you need the next layers out, the calorimeters. These are designed to stop particles and measure their energy.
Stop them. How?
They're made of dense materials. When particles hit these materials, they initiate a shower of secondary particles, and the calorimeter absorbs the energy of this whole shower. There are usually two main types.
Yeah.
First, the electromagnetic calorimeter, or EC. It's particularly good at stopping electrons and photons and measuring their energy very precisely. Then, further out, there's the hadronic calorimeter, or HCA. It's denser and designed to absorb hadrons, particles made of quarks like protons and neutrons, and others like pions.
So different particles dump their energy in different layers.
Pretty much. Electrons and photons stop early in the ECL. Hadrons punch through the ECL and stop in the HCl. By seeing where and how much energy is deposited, you get vital clues to the particle's identity.
Right, I see. But what about muons? You mentioned muons earlier.
Yes, muons. They're like heavy electrons, but they're much more penetrating. They often zip right through the tracking layers in both calorimeters without stopping.
So they escape the inner parts.
Often, yes. That's why the very outermost layers of the big detectors are the muon chambers. These are large tracking detectors, specifically designed to catch and identify the muons that make it all the way through the inner detector systems.
So you need that outer layer just for them.
Absolutely. Identifying muons is crucial for many analyses, including searches for the Higgs boson and other new physics.
Okay, so if you combine all that data, the track from the inner layers showing path, momentum, charge, the energy deposits in the calorimeters, and any hits in the muon chambers, you can build up a pretty complete picture of each particle coming out of the collision.
That's exactly the idea.
Yeah.
It's like subatomic detective work, piecing together the evidence from all the different detector layers to identify the culprits the particles produce.
But you mentioned billions of collisions per second. The amount of data must be just astronomical.
It is truly staggering. We're talking petabytes per year. Far too much to store everything. It's physically impossible.
So how do they cope? They can't possibly record every single collision, can they?
No way. This is where the trigger systems become absolutely essential. These are incredibly fast electronic and software systems that analyze the raw signals coming out of the detector in real-time fractions of a second.
Real-time analysis.
Yeah.
Of that much data.
Yes. The trigger system is programmed to look for potentially interesting signatures, things like particles with very high energy or momentum, specific combinations of particles like multiple muons, or patterns suggesting the decay of a heavy object.
So it acts like a high-speed filter, basically.
Exactly. It has multiple levels,
Yeah.
getting more sophisticated at each stage. It rapidly decides, is this event interesting enough to keep? It might look at hundreds of millions of crosslinks per second, but only selects maybe a few hundred or 1,000 events per second for permanent storage.
Wow, so it throws away almost everything.
It has to. It filters out the vast majority of relatively mundane, well-understood collisions to focus the limited storage and analysis resources on the rare events that might hold discoveries.
Okay, so they've triggered on an event, stored the raw data for it. What happens then? Does someone just look at the raw signals?
Not quite. The raw data, which is basically just electronic signals from millions of detector channels, needs to be processed. This is called reconstruction. Complex software algorithms run on massive computing farms
Okay.
to take those raw signals and translate them back into physics objects. Reconstructed particle tracks, energy deposits, identify particles like electrons, muons, jets of hadrons, and so on for each selected collision event.
So turning the electronic signals into a physics description of the event.
Precisely. This produces large data sets of reconstructed events. And this is the data that physicists around the world actually work with.
Ah, so this is where the global collaboration really kicks in, using this process data.
Absolutely. The data is distributed globally using the worldwide LHC computing grid, a massive network connecting computing centers at universities and labs across the planet.
So researchers anywhere can access it.
Yes. Thousands of physicists access this data. They run their own analysis code on these millions or billions of reconstructed events. They're looking for patterns, making incredibly precise measurements of known particles and processes, searching for extremely rare decays, or hunting for tiny statistical bumps that might signal a new particle or a new force of nature.
It's a huge collaborative effort, sifting through mountains of data for those potential needles in the haystack.
It really is. It requires immense computing power and sophisticated analysis techniques developed over many years by this global community.
So if we recap the whole journey, start with hydrogen, boost the protons through a chain of accelerators, inject them into the LHC, use superconducting magnets to steer them, and radiofrequency cavities to accelerate them to near light speed.
Uh-huh.
Then use special magnets to squeeze the beams and collide them head-on inside massive layered detectors.
Right.
The collision energy creates a shower of new particles, some stable, some decaying instantly.
Yep.
The detectors track paths, measure energy, identify the particles layer by layer.
Correct.
A trigger system rapidly filters the billions of collisions, saving only the most interesting ones.
Crucial step.
That raw data is reconstructed into physics events, distributed globally, and analyzed by thousands of scientists looking for discoveries.
I've got it. That's the essence of how the LHC operates, is this incredible microscope our sources talk about, probing the fundamental fabric of reality.
It really is an astonishing process, from start to finish, smashing things together at incredible energies and meticulously sifting through the debris to understand the universe at its smallest, most fundamental level.
Indeed. It connects the tiniest scales we can probe with the largest scales of the cosmos and the earliest moments of the universe.
It's quite profound when you think about it that way.
Yeah.
How this research into the building blocks shapes our entire picture of reality, which leaves us with a final thought, perhaps.
Yeah.
If they do definitively find particles beyond the standard model supersymmetric partners or dark matter candidates or something completely unexpected, what would that actually mean? How could discovering one new particle fundamentally change our entire understanding of the universe and everything in it? What else might be lurking just beyond our current view?
That's the million-dollar question, isn't it? Or maybe the trillion-dollar question. It would open up entirely new avenues, force us to rethink our most basic theories. It's what keeps everyone searching.